Hello, everyone. I'm Yutian Chen. Today, Richard and I are gonna give a tutorial about language modeling for optimization, and specifically in the context of AutoML. So, undeniably, in the past few years, the large language models and the transformer as its backbone architecture has been mm, introducing revolutionary changes to all different kinds of machine learning areas. It starts as language models and then quickly extended into other sub areas like image and video generations and audio synthesis. And recently, it has also introduced into the control and the decision-making problems. All of these successful applications are start from this seminal paper, the transformers or the attention is all you need. So this paper has already got over 88,000 citations so far. And this is this introduction of the powerful architecture enables all different kinds of abilities we have seen from very successful products such as ChatGPT and BART. One of the very kind of outstanding features of the transformer and the language model is so-called the in-context learning. By what it means that instead of learning the parameters of a machine learning model for particular tasks, we can give the model to adapt to a new task through the input sequence without changing the parameter of the model at all. So in this diagram, in every column, it gives the sequence or input sequence of some new task, a few demonstrations or the examples of different tasks. And after seeing this example, the language model is able to answer, to learn the skills embedded by these provided from the input sequence and output the questions for output answer of a new question from the same task without changing the parameter at all. And another advantage of the transformer model is that people have introduced all different kinds of ways to build a unifying interface so that the language model is not only being able to deal with text, but can be generalized to all different kinds of modality of data. For example, we can use combine the input from the text and the images, videos, and also some control signals such as the actions of robotics or even some audio signals into the same model. And a single model is trained to be able to understanding and also even outputting different modalities of data at the same time. So in contrast to all these tremendous changes the large language models have brought to different kinds of areas, we feel that the research of the language model and the transformer architecture in the AutoML area is still sort of kind of underexplored yet. And we are very looking forward to some kind of GPT moment where the language model can be applied to AutoML to let us to have a much better kind of automated and human-friendly interface in the AutoML pipelines. So this is a very quick kind of introduction to AutoML. I'm pretty sure most of you have already been familiar with the concept. So in the traditional machine learning pipelines, we have all different kinds of steps that requires manual selection or the design choices that requires expertise knowledge about how to process data, how to do the feature engineering, and what model to choose given a new task, etc. And the task of AutoML is to automate part of those steps. For example, the hyperparameter optimization would like to automatically choose the optimal hyperparameters for a machine learning model. And the neural architecture search tries to identify the optimal network architecture given a new task. And meta learning tries to learn a more general and the learning algorithm, or sometimes the initialization of some machine learning models. In all of these different sub-problems in AutoML, a lot of problems can be summarized as an optimization problem, where given a new task with the training and validation data set, we would like to optimize some metric. For example, the metric is some, for example, like when we train the model on the training subset, and then we evaluate the trained model on the validation data, then the metric is something we care about. For example, it's the accuracy in a classification model or the L2 loss in a regression problem. Then we would like to optimize this metric with respect to some design choices. So depending on the problem we study, the design choices can be the choice of the hyperparameter values or the network architecture, or in meta-learning case, it will be the optimization algorithm, etc. So because the metric we want to optimize usually involves a lot of components in the machine learning pipeline, it's hard to, like in a lot of problems, it's hard to get the gradient information. So a lot of problems in this domain can be abstracted as a gradient-free optimization problem, or people can usually consider it as a black box optimization, because all we observe given a design choice is the single metric scalar, and we don't have additional information about that. So in order to solve this problem, there has been many optimization algorithms that has been designed in the literature, such as Bayesian optimization, particularly for hyperparameter choice optimization, and the reinforcement learning and evolutionary strategies are used a lot in NAS. And also the genetic algorithms is also very commonly used for optimizing this gradient-free optimization problems. So talking about language models, what can the language model really bring us? What kind of benefit we can earn from language models if we will consider the problem, especially the optimization problems in AUTOML? In this tutorial, I would like to take two different aspects to introduce the benefit of using language models for and talk about a few problems we could potentially use it to solve. So in the first part, I will first talk about the transformer architecture that's behind the current large language models, how we can make use of this powerful modeling capacity, and also the in-context learning I have mentioned at the beginning of the tutorial, like what kind of benefit we can get by adopting this transformer architecture for solving optimization problems in AutoML. And in the second part of the tutorial, Richard will talk more about how to, like, what kind of knowledge the pre-trained language model encoded will be useful for AutoML problems. That is going beyond just the network architecture, but also the additional kind of human knowledge that can be consumed in these language models. So the outline of this tutorial will be in 4 parts. I will first introduce the basic concepts of language modelings and transformers, and then talk about a few examples of how to apply the transformer architecture into the optimization problems. And I will go through a few examples in the literature that has already started using transformer architectures. And then Richard will talk about more open problem, like how we can make use of the large language models, particularly with its kind of contextual information in solving or improving the optimization algorithms. And this tutorial will be concluded with some more discussion about the future visions and open questions. So all these successful stories start with this seminar paper, the transformer paper. The first architecture of the transformer has the encoder and the decoder components. Take an example of a translation problem from English to French. Given an English sentence, I arrive at some place, we'd like to train a model to translate into French. Then for the transformer model, the encoder will take the input sentence as input. Then it will go, all these words will go through several blocks of the attention blocks and process and learn a better representation of the input. For example, for these 4 words, I arrived at then the encoder, at every layer, the encoder will process every word separately, but then the information for every word will be attend to the latent representation at the lower layer from all the words in the input sentence. After we learn the representation from the encoder, we will send that to the decoder. the decoder is very similar to the encoder architecture. The only difference is that we process the decoder word by word. What I mean is that the decoder generates the outputs autoregressively. We've given the input information from the encoder. The decoder will first predict the first word, conditioned on the latent representation from the encoder. And then given the first word, it will use the information from the word that just generated and all the latent representation from the encoder to predict the second word, and then repeat the process. Then at every step, the decoder will only attend to the word that has already been generated and doesn't have the access to future words it's going to generate. And the key component in every attention block in both the encoder and decoder is this attention-based attention mechanism. So what the attention is basically in every layer of the attention block, and there's one token corresponding to one input word or subword. And every token will generate 3 vectors. We call it query, key, and value vectors. So the output for every token at every block will be a weighted combination of the value vectors from all the tokens in the sequence. And then this combination weight is a softmax that measures the similarity between the query vector at the current token with all the key vectors from all the tokens at the same level. So that basically measures similarity. Like if 2 words are similar with each other in its semantic meaning, then it will put more weights on the similar weights token when we generate the output of at the current step. To make the architecture even more powerful, the transformer introduced this multi-head attention. Instead of putting the majority of the attention at one location, multi-head attention allows every block to attend to several different locations. Maybe one location is focused on one like time information, and the other head is focused on maybe the location information, etc. So it allows us to attend. It allows it to attend several different kind of information at the same time. Because of the attention mechanism, the transformer is the vanilla structure of the transformer or the attention mechanism doesn't have the concept of time or the order in all the input tokens. It's just treated as a set. In order to deal with sequential modeling problems, people introduced the positional encoding that represents the order of the sequence so that the transformer knows which word comes before the other. So the original transformer paper was introduced to process text. For the input of the transformer, we have a sequence of text, and then it will go through 2 steps. The first step is to use a tokenizer to split the sentence into several words or subwords. Each is represented as an index in the vocabulary. And then we train an embedding table where it's basically is a matrix where every row corresponds to a learnable representation of some word. Then once it's trained, we use this embedding table to look up the corresponding embedding vectors for every word. The input format has been extended beyond text and into other domains, such as images in the image transformer or in the image vision transformer paper, and also it's been extended to audios. And recently, people have started to use it to process discrete or continuous features. When transformer takes the input and goes through all these blocks of attentions, then eventually we would like to use the output of the transformer to accomplish the real tasks. So there are usually 2 ways to use the output from the transformers. The transformer has been used to learn the representations of the input sequence. In that case, for example, in the BERT model, people provide a sequence of the words, then we use the encoder only in this case, and then the encoder outputs another sequence of vectors of the same length as the input, and then the output tensor at every location corresponds to one representation at the same step as the input sequence. So this embedding can be used and passed directly to downstream models. It can be a very simple linear layer for regression or classification, or it can be another transformer architecture to accomplish more complex tasks. And probably a more familiar way to use it nowadays is to use a decoder to generate the answer directly. For example, in the translation task, we were given the input, we will use a decoder to generate the output token by token. So instead of getting embedding, we directly get the answer from the output of the decoder. And this decoder runs by predicting one word or one subword at a time. And then eventually, after several passes of the decoder models, we will get the full answer for the specific task. There have been a lot of decoding methods in order to get a better or meaningful answers from the input. For example, the family of ancestral sampling method will generate one token at a time. And then people have introduced all different kinds of methods, such as temporal sampling, top case sampling, and nucleus samplings. The other approach is to try to find a sequence that can maximize the likelihood instead of like greedily generating token by token. So people can use like beam search or more advanced search algorithm to find the best kind of optimal sequence. So we have talked about the architecture of the transformers, the input and output formats expected by this model. Then one might ask, like, how, given this model, how we are really going to train it. So there are also several different ways to train it, depending on what we would like to get from this model. And in popular applications such as GPT and the PaLM model used by inside the BART, then we train the model using the so-called causal language modeling. What it means is that we use the decoder component only from the transformer. Given the input sequence, we train this model to maximize the likelihood to generate the input sequence. So we model the joint distribution of all the words using a chain rule and maximize the conditional distribution of predicting the next word given the past the previous words we have seen. And then another quite a different approach is called masked language modeling, such as those used in the BERT and its variant models. For this masked language modeling, the task is not to predict the next word, but for every input sequence, we randomly mask some of the words in the input sequence, and then we train the encoder to predict the missing words in the input. In this way, we are not doing kind of continuation or completing the sentence, but to predict what has been missing. And then in this case, we can get from the output of the encoder, we get a sequence of the representation aligned with the input sequence. And this is commonly used for representation learning. There's also a hybrid approach, such as that used in the T5 model, where we use both encoder and decoder. But we formulate the problem so that we still use the similar idea of masked language modelings, where for every input sequence, we will randomly mask some of the words in the input. For example, in the sentence of "Thank you for inviting me to your party last week," we will mask out for inviting and last. Then we feed the masked input into the encoder, and then we let the decoder to recover what has been missing in the input sequence. In that case, we are doing masked language modeling, but we are actually training the decoder to generate the answer token by token. Once we have the model, so the language model has been most commonly used in this pre-training and task adaptation case, where we would like to make use of the high scalability of the transformer model, train it on a very large and diverse data set. Then we can apply that to specific tasks as a downstream application. So there are usually two ways to train or fine-tune the models for downstream tasks. The first one, or is commonly known as pre-training and fine-tuning, which means is that given a data set of new tasks, for example, a translation problem from English to some other, like the French language, then we start with a pre-trained model, fine-tune the parameter of the transformer on this new data set. We either use supervised fine-tuning or use a reinforcement learning, try to maximize the reward we will expect to get from this language model's output. In contrast to fine-tuning, another popular way for downstream tasks is called prompting, which has been pioneered by the GPT-3 model, by the GPT-3 paper. So in that case, we don't touch the parameter of the pre-trained model at all. Instead, we freeze the language models and put all the information about the new task, including the task descriptions and the new data set, in a single sequence that is fed into the language model. And then we let the language model, the decoder part, to generate its answer. And then what's really used here is that the language model, once trained to complete a sentence, it will look at the information we provided in the prompt. Then it will understand that this is to translate, is a translation task. And then after it's seen the examples of those translations, it will automatically suggest what would be the translation for the last word at the prompt token. So this kind of new in-context learning ability is something I think it's going to be very useful for optimization problems in AutoML. So next, I will walk through a few works that has been explored recently in the literature of AutoML that uses the transformer architecture. As a reminder that a lot of optimization problems in AutoML can be summarized in this kind of simple optimization problem. And all we want to do is to solve this gradient-free optimization. And there's a very basic but important observation. I think this is going to be very useful when we think about how to use this in-context learning ability of transformer to solve a lot of optimization problems. Given a minimization problem, f of x, for example, we can consider this is hyperparameter tuning a problem where x is the set of hyperparameter values we want to choose, and then f is the model metric we want to maximize or minimize on the validation data. Then an iterative optimizer will take as input the current location of the search problem, the x, and the corresponding function metric f of x. That is when we take the hyperparameter value of x, train a machine learning model, and evaluate on some validation dataset. And there may be some additional information that comes from the past optimization trials, or it can be some additional prior information provided by the researcher. Then the iterative optimizer will output the next query point such that we can use it to train a new model. So when we use it to train a new model, we observe the information, the model metric y, t plus x, and then we will feed the pair of xy observation in the next optimization step and repeat. So when we apply this iterative optimizers repeatedly, we can see that the computation graph is very similar to a sequence-to-sequence modeling, where we take input. So the algorithm will take the input, a sequence of the observation, xy pairs of observations, and the output will always be the next query point, the x values at every step. This observation has been explored in the past learning-to-learn literatures, and people have started to use different recurrent neural network architectures. For example, in our earlier work of learning-to-learn without gradient descent by gradient descent, we use LSTM to train neural optimizers. But then we found it has very limited ability in modeling long sequences, and then it's not able to generalize beyond the different dimensions of the hyperparameter tuning problem. And then besides predicting the next query point, since we already have this formulation, we can see that it's natural to probably also train the model to predict the next function value. So that is as if we train the model to predict like the model metric as if we use it to train a real model. So this kind of few shot function regression ability will be very useful for a lot of like non-gradient Fourier optimization problems. So next, I will talk about different works that have been explored to use transformers to do either sequence input optimization or the function, or use it as a function surrogate. I have mentioned that we can use transformer models either to fine-tune the models to learn and adjust its parameter to learn per task. So that is the more standard meaning of like machine learning models, where we always train a model and learn it per task, and we adapt our model into a new task through its parameters. And then the meta learning idea is to make use of its in-context learning of the transformer, such that we don't change the parameter once it's pre-trained, and then let it to adapt to a new optimization problems in its context. And then depending on what we use the transformer for, we can classify its applications in either train the transformer as a function surrogate, or we train it as an optimizer directly to provide the next query point in our search problem. So next, I will give a few examples in the literature, and by no means this is a complete list of the work that have already used the transformer for AutoML applications. We would just like to give a few representative examples to inspire more research into this area. So we start with the meta-learning approach to learn a function surrogate. For example, in the hyperparameter optimization task, when we are given x-y pairs where x is hyperparameter metric parameters and y is metric, then we send a sequence of x-y pairs as an input sequence to the transformer. In that case, the context or the input context of the transformer is the sequence of observations. In the prior fitting network work papers, they have used this idea to train this neural network to predict the predictive distribution from a Bayesian model, such as a Gaussian process or Bayesian neural networks. By randomly generating a lot of training examples from either GP function samples or from Bayesian networks, the PFNs can be trained as an automatic model to provide the posterior inference of those Bayesian models in one forward pass. And it amortizes the inference time significantly. And for example, in the paper, they show that the PFNs can give a comparable predicting performance as the original Bayesian models with hundreds or thousands times faster than more traditional sampling-based algorithms. And in our AutoML work, we not only look at how to train the model as a function surrogate, but also train the model to predict both the hyperparameters as an optimizers. So in this case, we use the same concept of context, where it's a sequence of XY pairs that we just embed every dimension of the hyperparameters together with the function evaluation. And additionally, we will take some text information as input that I will talk about later in the language model part. So for the optimizer, we train it with real hyperparameter tuning experiments. From that, we are able to learn different prior information. So it's also kind of doing the Bayesian inference, but it learns the prior not from the GP priors, but from some real data that has been collected in the past hyperparameter tuning tasks. We find it provides better predictive likelihood and also the uncertainty calibrations than a GP model. The PFN work has also been extended to the tabular data modelings. In that case, the sequence of context will be the data, a sequence of data points where every data with multiple features is encoded into a single token. And they found that it yields hundreds of speed up on CPU or thousands of speed up in GPU with comparable performance to more traditional tabular modeling models. And lastly, the same idea is extended to a more general meta-learning context. For example, in the GP-ICL paper, they used a very similar idea for image classification, and they find very interesting phase transition in the meta-learning setup, where if we start with we pre-trained model with a few tasks, the model is kind of overfitted to instances in those examples. When we increase number of tasks, it starts to memorize the task that has been trained for. But when we increase further the number of tasks, it starts to show this learning to learn behavior and is able to generalize to new tasks that has never been seen during training. So in the meta-learning examples, we require that the model is able to remember, able to fit all the data, all the training data in a single sequence. So that apparently that has some limitation that if we have too many examples or every example requires too many tokens to fit in, then we are not able to provide that to the current transformer architecture. So people has also explored use of the transformers for the per task learning scenario, where every input to the transformer corresponds to one example. For example, people have started to use it for the nest to train a transformer for nest predictor, where we consider every node in the graph we are searching for corresponds to one token, and then they take into consideration the node operation types and the connections between nodes as input into the transformer. They found their method ranked the second among all teams in the CVPR 2021 competitions. And then in the tabular modeling applications, the feature transformer, FD transformer, consider all the features in one row that correspond to one data point as different tokens in the sequence, and then train the transformer for this to predict the classification labels. So we have talked about a few examples that use the transformers either as meta-learning or per-task learning for learning the target. But eventually, we would like the transformer for this optimization problem. We eventually would like to get the output as an optimizer. So we need to get what's the next suggested xt. So this idea of using the transformer as meta-learner has been started in the population-based optimizers. For example, in Lan et al. In 2022, they started replacing part of the evolutionary algorithm. For example, in this case, it's the Gaussian evolutionary algorithm, where in this population-based optimization, they need to maintain the Gaussian distribution to sample the populations. And in the algorithm, a key component is that after they generate the samples from one population and then get the function evaluation for every particle, the evolution algorithm needs to compute the weight for different particles. Higher weight is given to better particles, and then these weights are used to update the distribution for generating the next population. Then in their work, in our works, we replace this ranking component with a set transformer, and then we make use of the advantage that the transformer itself operates on the set. So if we randomly permute the order of the input sequences, the output is not changed, but just like permutated in the same order. Then they train this transformer as component of the evolutionary algorithms. Or when we trained on some synthetic functions with up to 10 dimensions, we find this optimization algorithm is able to generalize to optimize hundreds and thousands of parameters of a neural architecture, of a neural network that's used to control many RL optimization tasks. And also, when we measure the performance, it outperforms a lot of recent evolutionary algorithms as well. So this tremendous generalization performance is very outstanding in this meta learning case. And a similar idea has been generalized and extended from evolutionary algorithm to genetic algorithms. And back to the optiformer, as I mentioned before, we can use it as a function surrogate, but we can also train it to predict every hyperparameter dimensions. In that case, we not only use it as a surrogate, but also the optimizer directly. And the context or the input sequence that feeds into the causal transformer, not only the pairs of the XY observations, but also some textual description of the task. For example, if we know that this is to optimize some convolution network for image classification, we can just describe that in text and feed that in together with all the other numeric values. We can also describe a lot like hyperparameter configurations in the same input sequence. Then we train this transformer to predict the function value given a new hyperparameter queries as a surrogate. And also we train this model to predict the hyperparameter values for the next query an optimization algorithm is going to propose. At test time, the optiformer will sample the hyperparameter value one by one. And then after we collect all the set of hyperparameters, we send it to train a new model, receive the model performance, concatenate all the hyperparameter value and model metric in the new input sequence, and then repeat the whole process again. So we find that by training this with behavior cloning, it is able to imitate 7 different hyperparameter optimization algorithms using the single model. And then we can tune the behavior of the algorithm through the prompt. Additionally, we can make use of the information encoded in the function surrogate part. And at every time, we sample multiple hyperparameter suggestions and then use our Y prediction, the function prediction power, to find the best, most promising hyperparameter queries. We find that improves the quality of the proposal. And then in those out-of-domain test examples, we find this sample and ranking algorithm is able to become even more powerful than Visual optimizers that's based on the GPU CV algorithms. For some training algorithm, it has never seen during training. We also explored multi-step plannings for transformer in another work. So I have given a few examples in this in different combinations of either using the transformer as surrogate or as optimizer directly in either the meta learning setting or learning per task settings. Although the research of transformer-based AutoML is still in very early days, but we have already seen a lot of sort of performance in many problems. So I think this is a very promising research area for more exploration. Next, I'll hand over to Richard to talk about more like how we use language models, not only just transformer architecture, but the language models for AutoML.
Hi. So in contrast to what Yutian talked about, which is basically trying to turn numeric objects into like tensors and directly sending them to transformers, I'll more be talking about how you can interface with the current large language models, and which can be more restricted, right? Like for instance, you cannot change the tokenization of GPT, for example. So I believe that language can be an interface for AutoML in 2 basic general ways. The first one is an end-to-end pipeline understanding, right? Where the LLM can potentially understand the entire pipeline of your AutoML system. And the other part is that an LLM can potentially be a user-based system interaction. Sorry, one second. Yeah. And so in contrast to previous works in the LLM community, I think that AutoML has some distinct data types that I don't think people have been touching recently. But basically, the first set of data that might be of interest is textual data, but this is actually very different from the normal textual data that's commonly seen from like, books or whatever text that LLMs have been trained on. Because for instance, the textual data in AutoML might be very like sparse, it might be very weird formats, things like that we need to look into. Another set of data might be structural data. So this includes things like the classifier architecture, right? A lot of us do narrow architecture search. It might be useful for the LLM to actually also understand these kinds of components. And even things like evaluation code, right? For instance, if we're trying to do hyperparameter tuning on like a CFAR10 training task, it might be very helpful to let the LLM see the actual evaluation code, right? The actual training code. That might give a lot of context on what the objective function is doing. And last but not least, this is a big issue that I don't think has been resolved in LLM literature, is how do you process numeric data, right? So far, the LLM community has only really looked into things like, can you add two numbers? Can you multiply two numbers? Things like that. But right, as AutoML researchers, we use far more complicated mathematical structures. And also the LLM community has only studied things like symbolic math, generally speaking, right? Like if you can read some sort of math competition problem and using symbolic manipulations figure out certain answers. But I don't think they've looked at like very hardcore numeric abilities of LLMs. So the first case study I want to show is, for example, NAS. Okay, so on the left is basically some of the more common techniques you have with function prediction or performance prediction techniques. So let's take a look at this. So on the left, people usually have tried manual encoding. So what this means is that you're going to take an architecture, right, NAS Bench 101, and you're going to turn it into some sort of, I guess, path encoding, right? You're going to try to do some mathematics and then convert this architecture object into like a fixed length sequence, like a path encoding, maybe of like I think 0 and 1s. And then you're going to send it to an MLP to predict the objective value, right? So there are a few issues here that have a lot to do with lack of transferability, right? So for example, you need this encoding to be a fixed length. Otherwise, the MLP can't process all these like variable length tensors. The other part is that a lot of times this is domain specific. As in like, if you have another NAS benchmark, which might be like slightly different, you already cannot, it might be very hard to combine those kind of encodings to have some sort of more general performance predictor, right? So there's a key issue here with the manual kind of setups is that there's low transferability. Like you have to write one system for NAS Bench 101 and then another system for NAS Bench 201, things like that. But hypothetically, right, I don't think this has been explored yet, and I wouldn't know if this works or not, right? But hypothetically and ideally, perhaps you can exploit the length independence of the LLM, and basically you can represent your neural architecture as this text instead, right? Text does, and the fact of the matter is the LM doesn't care about the length of the text, so you can have any variable length text. So in principle, maybe it's possible to combine both all these different NAS benches together with a single, maybe common systematic representation in terms of text, let's say, and then have a more unified function predictor, right? Therefore, you can train over multiple tasks in AutoML, which I think was a huge restriction before. However, a key issue here is that token-based numerical understanding is actually still very poorly understood. So this is a screenshot from ChatGPT 2022. I wouldn't know how it is in 2023, but I think the point still stands, right? Someone sends in a basic math problem, and then the AI got it wrong, right? It cannot do like certain basic addition sometimes. And so there's this like mysterious problem here where the idea is like, well, is this a problem with tokenization? Maybe it is, right? So one question you might ask is, let's give an example. How do you tokenize the floating point number 0.45, right? So there are a lot of different ways. The first one is positional, which is the most common thing that's being used in all these LLMs. And maybe you want to be more fancy and try like scientific notation. Maybe it has its ups and downs. I think people have tried this before with varied results. And some people have even tried like a word type tokenization where they represent it as literal words because, well, if we train with an LLM that's trained on words, then clearly this might be even better, right? And for customized LLMs such as like the Optformer, we actually instead can use our own vocabulary, right? We don't have to stick with the default what's called a sentence-piece vocabulary that almost every LLM uses. We can inject our own custom tokens in that vocabulary to represent numbers. This is very common with like previous works that don't like train on English but train on a bunch of this kind of somewhat numerical data, right? So for example, you can represent scientific notation as this instead, where you have these like custom plus token, custom mantissa token, etc. And you can also normalize and bin, right? You make every floating point number go between 0 and 1, and then you bin it between like 0 and 1,000. And so, for example, like 45 here represents, I think, 0.045 in that binning context. So one challenge here is, well, how do you compare the two types of tokenizations, right? They both have their pros and cons. So the standard tokenization, right, the positional and maybe scientific ones, it's easier to interface with pre-trained LLMs, right? All these like GPT models and Palm models, right, if you're using their kind of tokenization, then you can easily interface with them. And it, of course, will require less string pre-processing, right? It makes your life easier. You just literally send in that floating point number. But sometimes, as people have seen in previous papers, this is somewhat of an unnatural representation for models. Because, for instance, positional encodings of floating point numbers, like you don't know when they end, right? You're going to force the model to say, basically, when it tries to output the floating point number, you need the LLM to figure out for itself when it's to stop. This might be kind of unnatural, and it might be hard for it. And also, there are certain difficulties of parsing these kinds of outputs, right? Like, it might be easy if like the LLM outputted just the floating point number, but if you had some sort of like brackets or dictionary or something like that in Python, this gets infinitely more hard. So as for custom tokenizations, right, these have some benefits such as controllable properties, right? Like if you use a customized tokenization where you represent every floating point number in like with only 3 tokens, then you can always expect the decoding output is 3 tokens. And you can also expect that, okay, the middle location of that tokenization is always the mantissa of the number, or like the final token of that decoding output is always the exponent of the number. So of course, it makes this easier to decode and serialize, right? And also, with these kinds of customized versions, you can actually compute explicit numeric distributions, right? You can basically look at the distribution of the token outputs, and therefore this leads to a distribution, like you can turn it into a TensorFlow probability object or whatever, and do some probabilistic kind of post-processing. But of course, then if you use your custom tokenization, it's kind of hard to interface with pre-trained LLMs. And this is especially the case with decoder-only models such as GPT and the Palm, because they are literally using one single vocabulary the entire time. So this means that it might lead to lower transferability between different tasks, right? Let's say you're training on an AutoML task, and you also want to have it understand English better, so you're going to try to train it on some English task. Well, you might have different tokenizations, and so this might cause lower transferability. So this is a deep challenge going on, and I can also extend it to certain mathematical structures, right? Because tokenizing certain more complicated mathematical structures is still poorly understood. So for instance, as I mentioned before, how do you properly tokenize like a direct acyclic graph, a DAG, or a NAS graph? Or for example, if you're doing combinatorial search, how do you tokenize those kind of objects? And lastly, right, a lot of us do some sort of constraint optimization, right? Like we're optimizing again around the simplex, right? How am I going to represent that as like a text or a list of tokens? Yeah, and then this is also a very common issue is constrained decoding, right? When I'm playing with Bard or sometimes even ChatGPT, if I ask it like, what is 2 plus 7, and just please give me the answer, it doesn't give me just the answer, right? It literally starts talking, rambling on about like, he ran a Python code to calculate the what is 2 plus 7. So that can be pretty infuriating, especially for AutoML researchers who want just the number, right? And so there are a few ways around this. They're not all like, it's not all universal. So for example, for custom trained LMs you're doing yourself, there's tricks such as vocabulary logic masking. So this means that you sample a subset of tokens at each step, right? If you know that you only want to sample the numeric tokens, then you can mask out the non-numeric tokens, like the English tokens, to always obtain like the numeric token, some sort of numeric token, right? So you can only you can just sample the digits only. And also, you don't have to use a transformer-based decoder. You can always use a custom-based like sampler or a neural network with just a transformer encoder, right? This is a very common thing. So for example, I'm just going to use the pre-trained English encoder and attach it with an MLP to obtain a actual floating point output always. But when you're interacting with things like PaLM and GPT, your only API is to interact with it through like basically text, right? You can only send in text, generally speaking. So there are a few ways that the LLM community has made some tricks to make this work. So the first one is prompt engineering, right? Like you can try to pray and tell it, please give me the number and please convert your reply into some format. And with some chatbots, I even had to threaten them, like, to get it to work. So you can try that. But of course, if you want it to be not just a floating point number, but like some sort of JSON-like format or some like parent-like, right, like a dictionary-like format, things like that, this requires really advanced regexes, especially in the AutoML field, right? Because you're dealing with hardcore numeric optimization. There are other ways, such as fine-tuning, where you just try your best to show training examples of the correct format, right? I mean, this is only going to work if you have access to the LLM itself, which is like sometimes billions of parameters. So this might not be the most practical thing, but if you do have the access to the entire model, you could do this. And another thing, as I mentioned sort of before, is that all of these APIs do have an embedding service where you simply send in a string and then the embedding service returns a tensor, right? A list of NumPy floating point numbers. Then you simply use this, however you want, this embedding vector, right, into your custom decoder, just like before. But at least like they provide the service. So basically what I talked about before is all the actual hardships that I think we encountered when trying to apply LLMs to optimization, and they basically become somewhat of an open question. I do also want to talk about the vision, like the sky-high vision, right? I don't know if this is like currently practically possible or how exactly the roadmap will be, but we can always hope and have visions about this. So one thing hopefully that we might all want to see is perhaps there might be a ChatGPT moment of AutoML. So what this means is that, for instance, in the case of optimization, right, the user can provide a hint. Let's say, like, I have an objective function, and it's basically a sign function, but with an unknown constant, right? That already gives you a gigantic prior on what the objective function is. So then you tell the AI, well, can you help me obtain the argmax of this function, right? And so it's going to try some few proposals and basically pull off its in-context learning to hopefully get this, right? Technically, you can solve this in like one single trial. Right after one trial, you already know the constant. But like, right, with current GP and Bayesian optimization methods, right, who knows how long that will take because it doesn't have that prior. Or for example, a more application-based setting, I'm training a CFR10 model, right? Then, well, the AI already knows then that the accuracies are always within 0 and 100, right? That already also gives you a huge prior on the numeric output ranges. Yeah, or for example, right, I've seen one of this paper that tries to do this in a mathematical format is like, my objective has an upper bound of 1.0, right? Can you use this fact to improve your predictions, right? I saw some paper that tried to bound the GP using this. Well, if the AI could also do this, that'd be great. Also, you can potentially control algorithm behavior. So, for example, can you explore the search space for the first 50 trials, then exploit for the last 50 trials, right? Using text, you can try to force the AI to output some sort of intended behavior. This is already very big in robotics, where you can send in a command and the robot does something with its like legs and arms. I don't see any reason why we can't do this for AutoML. Yeah, and also this allows use of subjective metrics too. So for example, right, I'm on Vizier team, we're big on baking cookies. So sometimes people are not always going to return back a numeric answer, right? They're just going to say, this cookie recipe you gave me tastes terrible, right? Can you please give me a better recipe with whatever, less salt? And so maybe the AI interprets this and can actually still perform this kind of subjective optimization. And yeah, also things like flexible search space descriptions, right? With words, you can easily say your constraint, such as like, my constraint is the disk x squared plus y squared is less than 1. Make suggestions only within this region, simpler. Or for example, with like, NAS-based or graph-based optimization, you can even say things like, subgraphs of some other graph with at most 10 edges. But basically the point is, hopefully using text, it can allow very flexible search space representations. Another thing so as Yutian mentioned, right, there's a Gato that sort of takes in all these different data formats with all these various encoders. There's also no reason why we can't do this with AutoML, right? So for AutoML, the relevant metadata information about maybe an optimization task maybe consists of things like the data set, right, if you're trying to optimize like CFR10 training. But you can also even send in maybe an image encoder, right? I can imagine someone drawing the plot of their objective function and saying, my objective function looks like this, can you optimize it, right? They might send it to an image encoder, right, just for fun. That's less serious, but I'm just giving a point. Other things such as the architecture, right? If your optimization objective is training some sort of architecture, well, it might be helpful if you send the actual architecture representation, right? Because sometimes when you inspect an architecture, right, you immediately know whether it'll work or not, because let's say it's not using batch norm or something like that, right? That's a very common thing for practitioners. I think AutoML systems can also do this. Yes, code, right? We have a lot of code abilities now in LLMs. We can use this fact to also look at objectives which are based on like code, such as some sort of training pipeline. Another one is math, because right, OpenAI I think released that one paper that's about LLMs now being able to read in symbolic math through LaTeX. For example, maybe the user can also input this as a hint, right? Let's say my objective are all quadratic functions, but with unknown coefficients. Then this already gives you a huge prior too. And of course, last but not least, the type of AutoML text. Yeah. One unifying theme here is the need for a better package to deal with this kind of data, especially for strings, right? So when I talk to practitioners of LLMs, they joke at how like they did this, PhD with like lots of theoretical math, but now when they work on LLMs, they just spend time like serializing and deserializing strings, right? And it's relatively easy for other subfields, actually, right? For text, usually you have some sort of human eval or maybe like a multiple choice type of question to do some more automatic evals. And for code, right, there's literally a function in Python that can take in strings and then interpret them as Python code. But I don't think this is so much for AutoML, right? For instance, like parsing this is a bit difficult already, right? Like how are you going to write a regex for this kind of thing, right? This already looks kind of daunting. And even more complicated structures like graphs, right? If you have this kind of format, how are you going to do that as well? And you can argue, yes, like JSON might be one way, but JSON has a very specific kind of format where it shoves in a lot of like redundant things like colons, brackets, things like that, that might overload like the sequence length, right? You're always limited by the sequence length, and you don't want to shove in too many like superfluous tokens. Another thing that I think could be done is we can all maybe leverage massive data across all of our like AutoML databases. So you can sort of see that an experiment is simply just an XY pair, right? Like you send in some sort of configuration and you get out some metric, right? And so like just as an ideal, maybe we can collect all experimental data from like, mankind. But as a concrete example, we can maybe save all of our AutoML databases so far and make it into a data set, right? The LLM community already even has a standardized data set that's basically all the internet scraped, right? The C4 data set. And so like, it's shocking how the entire internet data set is now standardized for people to work on, right? There's no reason why we can't standardize our gigantic AutoML data set. And also, this is very common already in the computational biology community, right? There's a ton of works I saw at last ICML where someone was predicting the property of some chemical given the chemical like strings or descriptions. So yeah, maybe what other AutoML data can we collect? It's not just X comma Y pairs. Maybe there's a lot more things given by other people at this conference. Yeah, and so I think we can also create new benchmarks for AutoML, where instead of just black box optimization, it's a lot more gray box now, where perhaps with if you're trying to optimize a function, maybe you can also provide the hint for that function, right? I talked a lot about this in this talk, but for example, the hint would be, my function is a quadratic polynomial with unknown coefficients, and then see how well your optimizers will do given this new hint, right? And also, with the inclusion of LLMs, I personally think that this allows optimizations in completely new domains. So, for example, much more so with programs combinatorics. So I know that evolutionary algorithms have been used a lot in that field, but I believe that LLMs can also provide even more flexibility, especially maybe like with these performance predictors on those kind of search spaces. And lastly, I do think that in reverse, we can also contribute back to the LLM community as well. So we can provide our own types of benchmarks for them, right? There's already a work that's called like Big Bench, where they try to all evaluate the performance of LLMs like, GPT or Palm. But I don't think any of the benchmarks have included things that are somewhat related to optimization. So for example, right, we already know how to perform this kind of optimization behavior. So one of them would be, can the LLM perform like a multi-trial conversation, right? This cookie recipe tastes terrible. Can you give me a better recipe, right? Maybe we can send in those kind of benchmarks to test how well the LLM understands, like, what does it mean to have a better object? What does it mean to propose a better suggestion? Another case would be, like numeric and combinatorial understanding, where you can provide things like more numeric data, rather than just like symbolic math, which is the predominant like test bed currently. For example, previous evaluations of some function were this, and that, of some quadratic function. Can you predict the output of this function at x equals 5, let's say? Or even, can you give me a 90% confidence interval on your prediction, right? I don't think LLMs are very good currently at like saying things about how confident am I really about this numeric prediction. Yeah, and maybe things like related to tool use within AutoML, right? We've already seen them be able to use like other types of coding tools, but if it can use like calculators better, it can use GPs better, it can use all these other AutoML systems better, that'd be also very great. Yeah, so that's the end of my section of the talk. Now it's time for questions. Well, yeah.
All right. Yeah. Thanks a lot to the two speakers. I think this was very insightful, and I'm sure there are many questions in the audience. It works a little bit differently than in the main room. For those of you who haven't been here before, there's a microphone in the ceiling. So yeah, whenever basically you have a question, just raise your hand, and when I point to you, then I activate the ceiling microphone, and then we're good to go. All right. So who wants to go first?
Way more random and worse than that.
Oh, yeah, maybe. I'm basing off my slides off of like how Google does it, and maybe like I didn't notice that GPT might be doing slightly differently. So sorry about that. We can change that. But I guess the main point may still stand. Like you're all using specific types of tokenizations. Yeah.
I think the one of GPT-3 or any GPT is even worse than that one. Makes way less sense.
Okay, that's good to know. Even more of a low-hanging fruit for us.
Just a direct follow-up. Can you comment a bit on how you did it in Optformer? Did you have to play a lot with that? Or?
So the Optformer was designed in a more customized fashion where the decoder always outputs a numeric token from 0 to 999. Once you have that, you can immediately map this back into the Vizier space through because it's a normalized value, right? For example, for continuous objects, you map it back into the unnormalized space, or for categorical indices, you just, right? And one thing that we did have to use was the vocabulary forcing. We had to say, I'm only going to mask out, all English tokens, but I'm also going to mask out potentially some of the numeric tokens that I know won't work, right? If I'm expecting this categorical parameter with 5 different entries, I'm going to mask out everything from 5 to 999 and only turn on 0 to 4. So that one was actually a very manual forcing. There was no praying involved. Like no matter what the model's parameters are, it will always output some valid Vizier parameters.
You talked a lot about the connection of LLMs and then the optimization for the Optformer. Did you ever try using a pre-trained LLM and then fine-tuning it? Or was that actually the case for the Optformer?
So this is a really good question. So basically, Yutian, do you want to take this or?
Oh yeah, sure. So so far for Optformer, we trained it from scratch. So we haven't used the pre-trained language model yet. But that's a very good question, I think, because our transformer model is compatible with other pre-trained LLM models. So I think it's very kind of natural extension of this one. And another question is whether we can just use the pre-trained language models directly without any fine-tuning. There's actually a very recent paper coming out from Google Deepmind on arXiv that has explored this question. I think they have some kind of initial very promising results, and we are looking to explore more on to explore the fine-tuning pre-trained language models for optimization.
All right. There's some more questions over there. Maybe the one in the back first.
With me?
No, it's the one behind us.
So for the fine-tuning questions, I just want to know if it's possible to give the feedback to the GPT pre-trained model. So for example, if it give output the wrong answer, I will tell the ChatGPT that okay, the question was this, and your answer was this, and this is wrong. The correct answer is the other thing. So we ask the ChatGPT to correct itself. Is it possible?
So in terms of helping formats, I think this is one way. So for example, and one thing we're doing is with that example of the Bard kind of messing up and not showing me the actual answer. So what you can do is then you can say, well, you literally said this. Can you please reformat it back into a floating point number, please, right? And try your best and then, again, pray that it works. Sometimes it actually does. So I guess this is more like sometimes with these kind of LLMs, you have to double prompt it, where you say, okay, first give me a real answer, like first give me an answer, then I want you to turn it into this format, please, right? Emphasis on please. Yeah, so yeah, there are a few ways where you can try to like loop this and automate this kind of loop in the hopes that the format is correct. I don't know if I answered your question about this.
Yeah, my point is, I read somewhere that the ChatGPT is good at self-improvement, self-correction, right? So if we give some feedback, we tell him the right answer many times, maybe with some examples. So maybe, I don't know.
Yeah, I think the paper that Yutian mentioned did try this. Like here are some examples of the output I really want you to make, like these formats, and then please do it. And then I think it somewhat worked. Yeah.
Okay, then that's probably a question right in front of that.
Yeah, so question related to the XY pair. Have you thought about considering Y not just as the metric value, the average over all the validation samples, but having the LLM actually look at the specific data points in the validation set and what is predicted and what is the ground truth to have a better understanding of what kind of mistakes are made with that specific architecture choice X?
So I guess you're talking about like, in the optimization case, let's say I'm optimizing a CFAR10 training pipeline, and I don't just see the average accuracy over all pictures, but just also one accuracy over one picture, right?
Exactly.
I guess that's the question. That seems kind of hard to even pull off because of these kind of restrictions between like encoders and decoders, right? Like our decoder can only, do this numerical processing. So yeah, it'd be very hard to like send in that picture, right, into the transformer. You'd have to attach a vision encoder, and then it becomes like somewhat of a Frankenstein kind of.
Yeah, more related to the Gato example.
Yeah. So this may work if we really set up some sort of Gato in AutoML, but who knows how far we are from that.
Yeah, it's more about the vision, but.
Yeah, I want to add some more comment. I think this is a very good idea, especially if we have few short data. Maybe we can just like, in providing the X could be a little bit challenging. We need to like customize the encoder. But if we have a set of like 10 Ys, we instead of giving just one average accuracy, we can give like 10 Y, like the ground truth label and the corresponding prediction. Then maybe the transformer will look at multiple trials and figure out like maybe when I use like hyperparameter set 1, I get the first 3 correct and the last 2 wrong. And for the next set, I have like first 4 correct and last 1 wrong. Like maybe it has more information about validation set, and it could potentially give it a better way to propose the next set of hyperparameter. I think that could be something to try. And the transformer itself is like kind of compatible with this. We don't have a restriction to how many tokens to use per X or per Y. Yeah.
Let's do the following order. We take the question 2 lines back first, then we go with Alexander, then I think Joaquin was next, and then we go with Frank. Okay, let's start with that.
Hi, thanks for the talk. It's great. So you spoke a little bit about tokenizing numerical values, and the tokenization seems to have an impact on how well the model performs, right? So I'm wondering, should we be attempting to teach LMs, language models, mathematical intuition at all? I mean, would it not be slightly better if you teach the model to formulate the problem and then speak to some mathematical API and just respond based on that instead of teaching it to crunch the numbers?
Yeah. So in the example I gave where like, for example, the user wants the AI to optimize a function, and then the user says, well, as a hint, I give you a quadratic function, right? It's just that for these kinds of examples, at the end of the day, you still need an LLM to read that, right? You might not directly use a text decoder to do stuff with this, but you still would need maybe like a strong mathematically understood encoder to understand this kind of problem, and then do whatever you want with the vector embedding of that text, right? So I would say you still need a transformer to really process this kind of stuff. And the real question is, can these transformers understand these kinds of hints, right? Yeah.
So I understand that you need to be able to formulate it that level of intuition needs to be there. But do we expect the language models to learn to actually crunch the numbers?
Maybe not. For example, like potentially instead of using any sort of like transformer decoder, you can just attach. You can even attach a GP to like the output of the encoder, right? Like I guess as a more hybrid example, you can use a language encoder, read the text, you get the vector, send this vector to a GP, and use some regular Bayesian optimization pipeline, right? So there are also these like kinds of hybrids you can pull off that, yeah, you don't need the transformer to take over everything, such as full numeric understanding. But I think it would help.
So next up was Alexander.
Yeah, thank you for the great talk. My question is, in the second part of the tutorial, you showed how we can use pre-trained LLMs to do AutoML tasks, or how we can go in that direction. And I wanted to ask you, are we already at a point where we can quantitatively compare these like LLMs used for AutoML with more traditional AutoML methods?
Are we at the, so the question is, are we at the point where we can compare these already pre-trained LLMs, you don't have to touch too much on them, against like traditional optimization methods, right?
Exactly.
So with that paper, like transformers as optimizers thing, like that Yutian mentioned, they did this comparison, and I think the summary of the results, well, like they evaluated on like a few objectives, like linear regression, some of the tasks, and they found that it can sort of like, it has a very rough understanding of like what a decreasing sequence of numbers is. But they realized there's like, I don't think it was matching at all like against any, very like standard algorithm, right? Like I think the current, basically if you try to probe ChatGPT and whatever right now and say optimize this function for me, however you want, just without fine-tuning, then I think the output is like, it will roughly understand what's a decreasing sequence. It will roughly understand some sensible things like, maybe, like I tried this actually once, right? It's like, it'll enumerate the entire search space. If I give a search space of a continuous range, it'll actually try to enumerate like, grid points on that and have them be distinct, but it doesn't have any very strong, much stronger than that kind of understanding of optimization. So basically, if you compared it with like any classical algorithm, it'd be terrible still. Yeah.
There's still a way to go.
Yeah, there's still a way to go.
Yeah, I think this is a very good opportunity for kind of the contribution of AutoML community to improve the LLM. Apparently, it doesn't have very good numerical understanding yet. So, what if we provide more kind of data set, like as part of this text corpus, to pre-train the language model or fine-tune it? It might give it like a lot more kind of numerical understandings. It will be useful for other tasks too. And on the other hand, like as we show, like by training AutoFormer from scratch, it does have very good kind of numerical analysis, and it's compatible even better than GP. So I think I'm quite optimistic that like fine-tuning language model or including the specific kind of optimization-based data set into this pre-training data set will be a very promising direction to go.
And Joaquin was next.
Thank you for the great talk. I was wondering what do you think is the most promising output modality would it be like generating code for AUTOML, or would it be like generating configurations or something else?
Can you say the first part of the question again?
Well, what's the most promising modality for the output of LLMs?
So the question is, what is the most promising modality of the output of a transformer for in context of AutoML? At the moment, I mean, like, for us, we do optimization, and yeah, there's a lot of other AutoML like subfields about like designing certain systems that I'm not qualified to speak for. But in terms of, let's say, the optimization and numeric part, I would say the most promising would be being able to express more, like being able to optimize much more complicated search spaces that you can't do with just like regular optimization techniques. So as an example, right, like already code search is a very painful thing to do traditionally because you have to perform some sort of mutation-based, revolutionary kind of setup for that. But LLMs can easily just output code that roughly makes sense, right? So these kinds of modalities, the most powerful ones would be, the most powerful usage would be being able to attack really like new search spaces you just simply cannot attack with traditional methods because it's too hard to deal with the formats using traditional methods.
Yeah, thank you very much for the nice talk. I have one question on data. So LLMs stand and fall with data, and in a former you used or you showed very clearly that that's also the case. You had this former version with BBOB and the one with HBOB, and then the one with the Vizier one. And that one was just dramatically stronger than the rest. And so it's really just data. And I'm wondering, how special is the Vizier data? Do you think we have any chance to mimic something like that in the open world? Or do you have a chance to open source some runs that were like a couple of years old that nobody cares about anymore? Or, yeah.
So, yeah, the question is like, how special is the Vizier data, right? Can people outside of Google like have their own kind of data set for training these opformers, right? So I don't know what other kinds of data are out there outside of Google. I guess like I just heard from this conference, right? Like AutoGluon has some sort of data set. OpenML has some data. The question is whether that's enough to also create your own kind of very useful opform model. I wouldn't know. Now the other question is maybe like other techniques to get this great, right? To basically match real world objectives. So one thing that's possible is potentially training an imitator model, like in the RLHF community, that's called a reward model, right? Training a gigantic performance predictor. Like even us at Google, maybe we can do that, training a gigantic performance predictor and then open sourcing that. Because, yeah, so the context is like we cannot open source the Vizier data because of lawyers, because it has a lot of private experiments, yeah, and lawyers would not like that. But for example, like we can potentially have some sort of giant performance predictor trained on that data set and then give it out to the community as well. These are possible alternatives. As for like giving the raw Vizier data, this is still in like flux, these kind of discussions, because like the only thing that really the lawyers are worried about is the names and descriptions within these trajectories. If we remove them, then what real use are they really useful at all anymore? Because you've just wiped out the description of what exactly you're optimizing. Who knows? So that's the current state of the data stuff.
So I know there's still a question from Alexander Sugar and also from Albert, but I'm very sorry. We have to end this session here in the interest of also the other authors and the poster session that's coming now. So let me thank the speakers again and join me, please. Right, and next up, our booster session.